Okay, hello everyone. Today we are going to learn lesson 3.1 on graphing relationships. So this is our first lesson in our new module on functions and modeling. So we're going to take a look today at how we can take two quantities and relate them together in a nice visual display on a graph. So the homework that is attached to this lesson is pages 91 to 94. And we're going to do numbers 1 through 20, but we are going to skip numbers 8, 11, and 13. So a couple of nice visual displays to get us kind of started here today and show us an example of the types of graphs we're going to look at today are, I kind of call them more like story related graphs than they are focusing on XY equations and things like that. So in this first example, I kind of show you that you could visually represent this scenario with Ramon. Ramon filled a balloon with water and the balloon popped and all the water spilled out. And if you take a look at how they've chosen to represent this, we're relating two different things in this problem. The amount of water that Ramon had in the balloon and the amount of seconds that passed over this period of time. So if you take a look at what happens with the shape of the graph, anytime we see something moving uphill, we know that we're increasing. And if you look at this label of water level, Ramon is increasing the water level in the balloon until all of a sudden it pops, and that is why the graph drastically drops back down to 0 for the level of water after it pops. In this particular example, we have a situation where it kind of shows that Kathy and her dog had some very different opinions about what was going to happen on their walk today. Kathy was taking a walk with her dog, but then the dog ran away, continuing on in the same direction, so Kathy went back to her house to get some help. So if we take a look at these two graphs, they show the difference between what Kathy's path would look like and what the dog's path would look like. This side is labeled as distance in miles that they've traveled, and this is the period of time that passed in minutes. And what we can see with Kathy is this increase shows that she was increasing her distance away from home walking the dog. But once the dog ran away, she turned around and went back home to get help, so the distance decreases and goes downhill, showing she went back home. However, the dog is starting out the same as Kathy, showing that the dog's distance from home is increasing over time until the dog suddenly gets a mind of its own, runs away, and the dog's distance continues to grow as it runs away from home in the same direction that they were originally walking. So we're going to take a look at a few questions that are similar to some homework questions where you're going to be presented with a situation and asked to match which graph provided goes along with the situation the best. So in this one, we have a bus that travels at 25 miles per hour and it slows and stops to pick up riders. The bus picks up riders at 2 stops. So if we take a look at these choices, we're looking for something that shows the bus at some point traveling at 25 miles per hour. We definitely want to show that it is slowing down to a stop to pick up riders, and it should stop twice. So one of the most common conversations we had in class is students that wanted to discuss whether it should be A or B, because graph C just shows that the bus continuously stayed at 25 miles an hour the whole time, never stopping to slow down and pick up riders. These two are similar in that you can tell that the rising and falling motion represents speeding up and slowing down to stop. But what we want to look at is the flat tops of these graph portions show that at least the bus did consistently go at 25 miles an hour for at least some point of its travel. So I think with them highlighting that this was an important number that the bus was traveling at, A would be more appropriate than B, because A at least shows that when the bus gets up to speed, it goes 25 miles an hour for a bit before slowing down to stop and pick up riders. In this case with the curves, it's like we speed up and as soon as we hit 25 miles an hour, we're almost instantly going back down in speed. So I think A would be the best representation of this situation. And then for step 2, we have a situation about a cook. The cook put broth and vegetables into the pot. Later he added some meat. He let it cook for a while, then served it to diners one dish at a time. So in this situation, we know that we should be looking for the level in the pot to increase as the cook is adding broth and vegetables, as well as when he adds meat. but once he starts serving it to diners, it's going to have to decrease at some time as he serves it out of the pot. So when we looked at this in class, a lot of students pointed out that the only graph that both increases and decreases is letter A. B only shows an increase in the level of contents in the pot. C only shows it decreasing. With letter A, we see kind of a sharp increase showing he added the broth and vegetables with a little bit of a pause where there was nothing more added. Later on, it goes up again when the chef adds the meat, and then he lets it cook for a while, remaining flat. And when he serves it one dish at a time, that's when we get kind of this little stair-step action at the end. So A would be the best choice for this one. Okay, so besides having to match some situations with graphs, there is some vocabulary that is very important to understanding the rest of this lesson. So I'm going to go ahead and flip my page to the extra notes on the back side, and we're going to look at 4 vocab words that appear in this lesson. Okay, first of all, a couple of words that are kind of partners to one another. We're going to be asked to talk about domain and range with some of our graphing situations today. So the domain of a graph is the set of all possible x values that could be included within the situation. So other words associated with domain and x values also include, sometimes we talk about inputs and outputs. The domain includes the inputs, or we also say it could be considered the independent variable. While range is kind of its alternate, it's the set of all possible y values that could be associated with a situation, and sometimes we call those the outputs or the dependent variable. Okay, and when we speak about our graphs today as well, we're going to be asked to determine whether the graphs we draw should be continuous graphs or what we call discrete graphs. So we've had some conversations in the past about this, how sometimes it's appropriate to connect the points on a graph and sometimes it's not. So the times where it is appropriate to connect the points, we're going to call a continuous graph, which will create a graph with a nice connected line or curve. However, when we don't find it appropriate to connect the dots, we're going to have a discrete graph, which is a graph with very distinct unconnected points. So we're going to take a look at each situation and practice stating domains and ranges as well. So what we're looking at now is sketching some graphs from some examples on page 90 of the textbook in the Your Turn section. And in this section, I'm going to take a look at the directions and make sure that we're very clear about all of the parts of the problem that are being required. So if I kind of look right here in the middle of page 90, the directions for this segment ask us to sketch a graph of the situation. Okay, we're also going to be asked to tell whether the graph is continuous or discrete, and then we're going to be asked to determine the domain and range. So we're going to take a look at problem number 5, where it says that at the start of a snowstorm, it snowed 2 inches an hour for 2 hours, then slowed to 1 inch an hour for an additional hour before stopping. And 3 hours after the snow stopped, it began to melt at 1/2 an inch an hour for 2 hours. So we're going to start every problem by figuring out what the 2 quantities that we are relating on our graph should be. In this particular problem, we were talking about inches of snowfall over a certain number of hours. So those are what are going to be on our x and y axis, and we need to determine which goes on the x-axis and which goes on the y-axis. So the x-axis needs to contain our domain or our independent variable, and in this case our independent variable would be the amount of time in hours that the snow is falling, and our dependent variable would be the amount of snowfall that we are receiving in inches. Another way I ask students to figure out which side should be which is, would we talk about how much snow fell per hour or how much hours per snow? If we would say snow per hour, then that tells you that snow per hour, whatever the per piece is your x-axis or your independent variable. So we want to always decide what it makes sense to count by as far as intervals on our axes. And we're not talking about a significant amount of time or a significant amount of snowfall in this problem. So I'm just going to stick to counting by ones. But we want to make sure we number each axis of our graph so that everyone knows what we were counting by and can read our graphs appropriately. And we're going to read back through each sentence and go ahead and start adding some points to our graph. So if we return to the first sentence of the problem, it said that at the start of the snowstorm, it snowed 2 inches an hour for 2 hours. So I think we can all agree that before the snowstorm started, we had not had any time that had passed. But if we're adding 2 inches per hour of snow, after 1 hour, we would have 2 inches of snow. And after 2 hours, we would then be up to 4 inches of snow. So this covers the first segment of the problem that said 2 inches an hour for 2 hours. And at this point, we can decide if this should be continuous or discrete. When deciding this, you ask yourself, would it make sense to connect this, showing that there could be periods of time and periods of snowfall in between this 1 to 2 inch gap? And I think we could agree that as snow is falling from the sky, it does not suddenly jump from 0 inches of snow to 2 inches of snow instantly. It definitely falls continuously and piles up gradually over time. So this is a situation that would make sense to include a line or a continuous graph. And then we're going to move on to the next piece of the problem. It says that after this point, it slowed to 1 inch an hour for an additional hour before stopping. So now instead of increasing by 2 inches per hour, we would only go 1 inch up over the next hour, putting us at 3 hours and 5 inches. Then it says that the snow stopped. When we say that it stopped, that means that we will have to show a continuous horizontal line so that the snow stayed at a consistent 5 inches while it was no longer snowing. And the problem states that it stopped for 3 hours. So I'm going to draw a horizontal line that stretches across a 3 hours time span. So it stops at 6 hours. And then it says that the snow began to melt, and generally it's not going to melt as fast as it fell. So it says that it began to melt at 1/2 an inch an hour for 2 hours. So over this piece, I would only want to drop 1/2 an inch in an hour and go ahead and drop another 1/2 inch over the next hour because it dropped 1/2 an inch per hour for 2 hours. And then we would stop because the problem gives us no further details. So we're not going to go ahead and predict what continued to happen with the snow. We're going to leave it at that. So the second question after graphing said, tell if it's continuous or discrete. And we determined that this one should be continuous because it makes sense to connect the dots and show all of the amounts of time and snow in between our points. And then we want to talk about how to write domain and range. So I'm just going to write D for domain and R for range, but what we're going to do is combine a really cool trick that we learned in the last module about compound inequalities, because we just wrote the definition down that domain represents all of the x values that are possible for this situation. So our graph gives a great visual if we ignore the y values for a moment and look just at our x-axis. I think we could agree that our graph stretches on the x-axis from 0 to 8 on the x-axis. And because of that continuous line, that means that anything between 0 and 8 could be a possible x value for our situation. So we learned how to write compound inequalities where we could place the x in the middle with our inequality signs, and we could say that our x could be any value between 0 and 8. And we can do the same with range, except for range discusses y values, not x values. So as far as range goes, if we cover up the x values for a moment, we can see that on our graph, our y values stretch between 0 to 5 inches of snow. So because it's continuous, that means that we could have anything between 0 and 5 for our range. So we're going to look at one more example to kind of show a little bit of contrast to this one. In example 6, we'll take a look real quick at what the book has to say, and we'll try that one. Okay, in number 6, says a local salesman is going door to door trying to sell vacuums. For every vacuum he sells, he makes $20. He can sell a maximum of 10 vacuums a day. So again, the first thing we want to do is decide what our two quantities being represented are. And in this problem, we have a gentleman who's selling vacuums and he is making money off of those vacuums. So our vacuums and our amount of money are going to be our two axes labels, but we want to get them in the appropriate place. So you have to think, does the amount of money depend on the vacuums, or do the vacuums depend on the amount of money? In this case, we would say the amount of money that this salesman makes depends on the amount of vacuums that he sells. So the money is the dependent variable and vacuums is the independent variable. Or otherwise I would say, would we say that this gentleman is making $20 per vacuum, or that he's making one vacuum per $20? So $20 per vacuum, the per vacuum is what would go on the x-axis. And I think again with vacuums, we're good counting by ones here because it says in the problem that he can only sell up to 10 vacuums a day. So we can number 1 through 10 without needing too large of a graph. However, if he's going to make $20 per vacuum and I count by ones, I'm going to have a hard time fitting numbers in an appropriately sized graph. So we're going to make this as easy as possible on ourselves, and we're going to count by 20s. So I'm going to label this axis by 20s so that everyone knows exactly what I was counting by. And then we've made something that's very easy to graph. One vacuum, he makes $20, two vacuums, $40, and so on. So there's an easy pattern to follow to create the points on our graph. But before we do anything else, we want to stop and think about whether or not it makes sense to connect these points or not. In this case, I would say it does not. If we connect this, we are saying that anything in between these points, like 2.5 vacuums, could be purchased for $50, when we know that no one can actually buy a partial vacuum. So in this case, this is a situation where we would want to state that this is a discrete graph, not a continuous one, and we would not connect the points. So we have to do domain and range just a little bit differently on these. We can't use our neat inequality trick on this one because domain is our x values, and I think if we look at our x-axis, we can agree that our points here can stretch from 0 to 10 vacuums. But we can't put the inequality and say x is anything between 0 and 10 because that's not really what we mean. We only can sell whole numbers of vacuums, not partial vacuums. So we would say that the domain would be whole numbers between 0 and 10. Same thing with range. When we want to look at the y values, and I think it's clear to see that our y values stretch from 0 up to $200, but we can't say that it's any y's between 0 and 200 because only these distinct points are represented. It is only the 20, 40, 60, and 80 that are possible values for y. So we don't even want all the whole numbers between 0 and 100, and 200. We would just say that it is multiples of 20 between 0 and 200. So that is how we graph relationships between a few different quantities.